Okay, hello Analysis 1A. We're going to go over Limits Review 1, which is just a bunch of problems. 17 problems, most of them were actually pretty easy. So we're reviewing what the right answers are, how to do the problems, how to think about them, how much kind of work to show. Alright, let's go. The very first problem is just maybe a little bit silly. It's the limit as x approaches 3 minus of x cubed minus 4x squared plus 2. And your first instinct when doing any of these problems whatsoever is to just see what's happening when x is approximately 3. Well, when x is approximately 3, in fact a little bit less than 3, but maybe that doesn't matter, then 3 cubed is 27. When x is approximately 3, 4x squared is approximately negative 36. And yeah, sorry, that's not 3 minus, that's negative 3, second try. So the limit, we're taking the limit as x approaches negative 3. And, okay, when x is approximately negative 3, x cubed is approximately negative 27. When x is approximately negative 3, x squared is 9, so that's minus 36. And this is just plus 2, so there's just absolutely nothing going on here at all. That's 9 times 7, negative 63, and 2, so it's negative 61. Okay, so have we learned anything? Not really. This is a polynomial. All polynomials are just completely boring and predictable. And in fact, it seems, and this is true, that if you take the limit as x approaches some number of a polynomial, then what you always get is just the value of that polynomial. Okay, more on that in another class or two. Okay, back to a problem that's at least a little bit challenging. The limit as x approaches 5 of 2x minus 10 over x squared minus 4x minus 5. Well, if you now try to just plug in 5 innocently, then you will get 0 on the top, and you will get 25 minus 20, which is 5 minus 5, which is 0 on the bottom. So this is a 0 over 0 situation. The numerator is approximately 0, the denominator is approximately 0 near 5. And so we don't know the answer, we can't guess it. So we have to do something, we have to kind of go back to work, as I say, and perform some kind of analysis. Here I think the analysis is just to factor, and indeed this is x minus 5, x plus 1. I think that's right. Yeah, so this is just a rational expression, and get the rest of the markers here. Since we're not interested in what is happening at 5, just what's happening near 5, then we can cancel, and we get the limit as x approaches 5 of 2 over x plus 1. And now it's no longer a 0 over 0 situation. If I plug in 5, I get 1/3, and so that's the answer to this problem. Okay, that was pretty easy. Let's squeeze another one in here, number 3. The limit as x approaches 2 minus of 3x over x squared plus 6x minus 16. Alright, well, let's see. If I plug in 2 in the top, I get negative 6. And if I plug in, sorry, that is 2 minus. So just positive 6. If I plug in 2 on the bottom, I'm going to get 4, and 12 is 16 minus 16 is going to be over 0. So I can tell you right now that that this is going to be some kind of infinity or negative infinity situation. So now what's relevant is whether that denominator is a tiny positive number or a tiny negative number. This numerator is basically just 6. So okay, let's go. There's a couple ways to do this. Probably the way that I maybe would do it is to just factor the bottom, or at least see if it factors. Does it factor? Yeah, it does. It becomes x plus 8, x minus 2, x squared. Sure. so that's pretty helpful because I'll just make a little sign chart over here. In fact, I'll just make a sign chart on the bottom. It changes sign at -8 and 2, and it's like a quadratic, so it's plus minus plus. Why is that? What does that tell me? It tells me that if x is a little bit less than 2, then for a number a little bit less than 2, this quadratic will be negative. And so, trying to squeeze some stuff in here. So basically, my conclusion here is that this numerator is going to be a little bit less than 6, but still pretty much just 6, whereas my denominator is going to be a tiny negative. And if I divide 6 by a tiny negative number, I'm going to get negative infinity. The other way to do this problem is if it didn't factor, well, if it didn't factor, then 2 wouldn't be a root, and then it wouldn't be anything worth talking about. But maybe you prefer this method, where you say the numerator is basically 6, a little bit less. And the denominator is, well, we can just do it, right? 2 squared is, well, I really do like my way better, but it's not wrong to say 2 squared is a little bit less than 4. 6 times a little bit less than 2 is a little bit less than 12, and then minus 16. So it is clear that we are at least adding a number that's a little bit less than 16, this is minus 16, is going to be a tiny negative. But okay, I like the factoring approach better. I think it makes more sense. Okay, good. Like I said, these are pretty straightforward. Let's do more. Maybe we can go a little bit faster or something. This is the limit as x approaches 0 plus of absolute value x over x. Okay, so what is this? Well, it's certainly a 0 over 0 situation. So what kind of 0 over 0 situation? Well, okay, I bet you can easily figure this out because, well, it's pretty much just 1, right? Ignoring the negatives for a minute, we're basically just dividing x by x. So it seems like it's going to be some kind of 1. And in fact, this is kind of just a silly problem because I'm taking the limit as x approaches 0 from the right. In other words, I can guarantee you that x is going to be a positive number. And so I think there are sort of 2 approaches that you can take here. Approach number 1, which is in some ways the best approach, is to actually just know the definition of absolute value. What is the definition of absolute value? This is something you have learned in previous math classes, but perhaps you weren't expected to really apply it in its full power until calculus. What is the absolute value of x? Answer: it's a piecewise function, and it tells you what to do based on whether the inside is positive or negative. So the absolute value of something positive is just that thing. And the absolute value of something negative is just the opposite. So sorry, I said that kind of weird, but this is perfectly right. If you want to know what the absolute value of something is, you just look at the inside. If the inside is greater than or equal to 0, it's positive, and if the inside is negative, then you just put a negative out front, making it positive. Okay, so this is the sort of analytic definition of absolute value, so they say. And therefore, what that means is that when you ever encounter absolute values in calculus, the thing to do is to just get rid of them. So this becomes the limit as x approaches 0 plus of, well, can I get rid of this absolute value of x? I can, because all I need to know to get rid of it is whether the inside is positive or negative, and in this case I can just say with certainty that the inside is positive. Because I'm approaching 0 from the right. So if x is a tiny positive number, then by definition the absolute value of x just is x. And so actually this whole problem is just this, and therefore the answer is 1. So there's really kind of nothing going on here. Another thing that you might be willing to do is to consider this as like a function that's worth knowing. This absolute value x over x function. It even has kind of a fancy name, the signum function. Signum. And what is it doing? It's telling you basically whether the function is positive or negative. And Why is that? Well, if you just make a graph of it, let's go. If you give me any positive number, then the numerator is positive and the denominator is that same positive number, and so the answer is 1. But if you give me a negative number, say negative 2, then I get 2 on the top and negative 2 on the bottom, so the quotient is negative 1. And so this is what this function looks like, and at 0 it's undefined. So we actually have like whole, and this is the function. Okay, so it's kind of an interesting function. It exhibits what in pre-calc A you would have called a jump discontinuity. More on that later. And so, in fact, the limit as x approaches 0 of absolute value x over x does not exist. This limit does not exist because from the left it approaches, that should say negative 1, and from the right it approaches a positive 1. But this problem only asked for what was happening on the right, so that's that. Okay. Good. More. So far these are all kind of very straightforward. 5. Here's one that's kind of strange, and maybe even you might say kind of annoying. This is the limit as x approaches 4 of square root of x minus 4. Okay, so there are only really two possible answers to this. It's either 0 or some kind of does not exist maybe because of something weird with the absolute value. But let's just make a graph of this. What is the square root of, what is the square root of x minus 4? It's just the square root function moved over 4. And so it looks like that. This is not something I think you could just sort of reason out on your own. This is in some sense a artifact of or a convention that we agree to. But I want to say here that this limit does not exist. And the reason is that I really, really like this rule that says that the limit from the left must equal the limit from the right. And so for our purposes, whereas it's true that the limit as x approaches 4 from the right of square root of x minus 4 is 0, certainly. On the other hand, the limit as x approaches 4 from the left of square root of x minus 4, well, here this limit just simply does not exist because we're here in analysis 1. This is intro calculus. We are only going to study the real numbers, so complex numbers, completely forget about them, throw them away again, and don't think about them at all. And so I cannot take the square root of a negative number. And so if x is a number which is a little bit less than 4, then that inside of this square root function is a tiny negative number, and I just can't take the square root of a negative number. So this whole thing just kind of falls apart, and this limit does not exist. Since the limit from the left does not exist, and the limit from the right is 0, it is helpful to just say that this limit does not exist. And therefore, that's what we say. Okay, so good. You might even find some other teacher, other textbook somewhere kind of answering this little tricky situation differently, but this is how we're going to do it. All right, I'm going to pause this for a second and go get some more coffee. Be right back. Okay, we're back. Number 6, the limit as x approaches 3 pi over 2 minus of secant. This is barely a calculus problem. This is essentially just a pre-calc problem. What does secant look like? Well, I recommend that you just know things. And I know that the graph of secant looks like this. With secant will be kind of infinite whenever cosine is 0, and cosine is 0 at pi over 2, 3 pi over 2, etc. And since cosine is the x-coordinate, cosine will be positive from negative pi over 2 to pi over 2. So the reciprocal of cosine will also be positive. So this is my 30-second attempt to teach you how you should probably just know this graph, like as well as I do. There it is. Therefore, what is the answer to this problem? If x is a little bit less than 3 pi over 2, then the answer is just negative infinity, and that's all there is to say about that. Good. You will notice, I guess if you're watching these videos in chronological order, that maybe this is a good time to make this comment really quick, that, actually, it's not. Let's keep going. 7, this is another trick. This is the limit as x approaches 3 of the 6th root of 81 minus x to the 4th. Well, this limit does not exist for the exact same reason as the previous problem number 5, but here maybe it's a little bit less obvious that you can only take the 6th root of a positive number. If you try to take the 6th root of a negative number, that doesn't work. And if you plug in a number which is a little bit more than 3, then the inside here is negative. And so the way to answer this question is to split it up into 2 problems. The limit as x approaches 3 from the left of the 6th root of 81 minus x to the 4th. Well, if x is a little bit less than 3, then x to the 4th is a little bit less than 81. So 81 minus a number a little bit less than 81 is the 6th root of a tiny positive, and so the answer to this is just 0. But if I try to take the limit as x approaches, 3 from the right of the 6th root of 81 minus x to the 4th, what happens? Well, now, if you give me a number which is a little bit more than 3, when you raise that to the 4th power, that's a little bit more than 81. So 81 minus a little bit more than 81 is the 6th root of a tiny negative number, and that just does not exist. So for the same reason I can't take the square root of negative numbers, I can't take the 6th root of negative numbers either. And therefore, sort of by our agreement that the limit from the left must equal the limit from the right, since the limit from the right, in this case, does not exist, then we say that this limit just does not exist. Okay. If you don't like that, sorry. Number 8. The limit as x approaches pi over 2 plus of tan. Okay. Good. Yeah, I guess I just recommend knowing the graph of tan. So, what does the graph of tan look like? Negative pi over 2, pi over 2. Tan is like the x coordinate over the y coordinate over the x coordinate. So, whenever the x coordinate is 0, there will be asymptotes. So, it's going to have the same asymptotes as secant. I think everyone knows what the graph of tan looks like. I hope so. All your pre-calc knowledge is just resurfacing here in calculus. If x is a little bit more than pi over 2, then the answer to this is also negative infinity. Alright, good. More. 9. The limit as x approaches infinity of 7x plus 19 over 4x minus 3. Okay, this is completely not new at all. This is the kind of thing that we did last semester, where we took the limit as x, we took the limit of sequences as n goes to infinity, but really it's just the exact same thing. This is a rational function. What happens for very, very large values of x to this rational function? I think almost everyone can just see it immediately that the answer is going to be 7/4. This is a linear on top and a linear on the bottom. But there is a method to demonstrating this, and that is to divide the top and bottom by the highest power of x in the denominator. The highest power of x in the denominator here is x, and so I can rewrite this as the limit as x approaches infinity of 7 plus 19 over x over 4 minus 3 over x, and these are all going to 0, and so the answer is 7/4. So by just performing this kind of algebraic move, this algebraic move of dividing by the highest power of x in the denominator is useful when you have a rational function, and specifically when you're taking the limit as x goes to infinity. Okay, I don't think I have anything more to say about that. Let's keep going. 10, the limit as x goes to 0 of e to the x cosine x, and this is kind of an unfortunate orthography here, or whatever, typography. But what was intended is this. So we're taking the limit as x goes to 0 of the product of these three things. Okay, so just don't overthink it, right? What have we just learned the previous class? We finally just learned, this very, very precise definition of a limit. And what was that very precise definition? Well, I'm not going to rewrite the whole thing now, but the limit as x approaches a of some function is L being a number, if and only if, and the answer that we eventually get is that, near a, the values of this function are very, very near L. So what is a limit? A limit is just a number. It's a number that the function is getting closer and closer to. So keeping that in mind, how am I supposed to deal with the limit as x approaches 0 of like all of these complicated functions all put together? Well, if limits are just numbers, then it seems like we can just settle this kind of one at a time, right? What is e to the x doing when x is really, really close to 0? Answer, when x is really, really close to 0, e to the x is pretty much just 1. How about when x is really, really close to 0, what can I say about cosine? It's pretty much just 1. And as x gets really, really close to 0, what can I say about the square root of 9 minus x squared? Answer, it's really, really close to 3. And so if I'm multiplying together three things, such that near 0, this one's pretty much 1, this one's pretty much 1, and this one's pretty much 3, then it seems like that the answer to this is just 3. And that's really just it. And actually, what this exhibits, so sort of preview or something like this, there is a limit law, which is really just a theorem about limits, and it's completely non-surprising. Here's what it says. It says that the limit, as x approaches a, of the product of two functions, in other words, take some function f, take some function g, multiply them together, ask what is happening to that product near a. Well, big surprise, it's just the product of whatever is happening at a and whatever is happening to f at a times whatever is happening to g at a. In other words, the limit of the product is the product of the limits. And if you just keep your self in the land of common sense, then this is just obviously true. Because limits are just numbers. So this function's going to some kind of number, this function's going to some kind of number, so these two functions are each going to those numbers near a, and so there we go. Okay, and that's kind of an application of that law right here. Good. This is a law that we can and will prove. I think later this week. All right. Pausing one more time. Okay. Number 11. The limit as x approaches 0 of sine 5x over x. All right. This is very similar to a problem we did in class, but now it's kind of a 5 instead of a 2. So all right, what's going on here? If I plug in 0, or try to plug in 0, I see, of course, that the denominator is going to 0, but the numerator is also going to 0 because if x is very, very tiny, 5x is still very tiny. Sine of something very tiny is very tiny. So we now, once again, we're in this 0 over 0 situation, but what can we do about this? I don't know. We better figure this out. I can't say that the answer is 1. In fact, the answer is not 1. Well, what is the answer? Well, okay. What do we know? What's our background knowledge? The background knowledge that we have is that the limit as x approaches 0 of sine x over x is 1. This is our fact. And we didn't really prove this, proof coming later. In fact, what we did was sort of sketched why we kind of very strongly think that it's true, and it's because for very tiny values of x, that's x and that's sine x, and they're kind of almost equal. Well, can I use this somehow? I think I can, because what this is really telling me is that the sine of some very tiny thing is basically just that tiny thing. So what I kind of wished down here was that this were a 5. And so what we can do is we can just multiply the top and bottom by 5. So if you multiply the top and bottom by 5, why is that helpful? Well, because now I get 5 times the limit as x approaches 0 of sine 5x over 5x, and this is then, this whole thing becomes just 1. Alright, so it's really just that simple, and if you don't sort of believe this or something, or you want to do something that makes you even more kind of confident, you could always switch variables. So you could do a kind of a variable transformation. You could say, let y be 5x, for example. And then you can observe that as x goes to 0, of course y goes to 0 as well. And so keeping these in mind, we may rewrite this problem as 5 times. So here I rephrase the problem as instead of in terms of x's, we just do it in terms of y. So this is the limit as y goes to 0 of sine y over y. And okay, I don't think this is really necessary to go into this level of detail, but this is certainly 1, and so that's what shows that the answer to this problem is 5. You can either do that variable substitution, or you can just kind of think about doing it. So alright, I think that's pretty good explanation. That's level 12 is pretty silly problem. This is the limit as x approaches pi of cosine x over x. And okay, this problem is just there to tell you that, you know, sometimes things are not hard. What is the cosine of pi? Answer -1. And so the numerator is going to -1, the denominator is going to pi, and so that's all there is to it. Good. 13. This is also not really a calculus problem at all. This is just an excuse to do a little bit of pre-calculus. What is the limit as x approaches 0 minus of our cosine? Alright, in a perfect world, every student would know the graphs of all the inverse trig functions kind of inside and out. Well, what does our cosine look like? I just know the answer looks kind of like this. So that's 1, and that's -1, and so if you take the arc cosine of a tiny negative number, that's pi up there, that's pi over 2, the answer is just going to be pi over 2. Yeah. Potentially you could also do a more, kind of take a more geometric approach by just sort of thinking about the unit circle and just sort of saying to yourself, okay, well, ultimately this is just a silly problem also, because this is really just asking what's the arc cosine of 0. And the answer is the arc cosine of 0 is pi over 2, because pi over 2 is when cosine is 0. So that's really all that's happening. Let's see if I can do the rest of these. 14, this is the limit as x approaches infinity of 7x squared minus 3x plus 2 over -5x squared plus 1. Okay, this is just review again from last semester, because once again we have a rational function. Once again, we're taking the limit as x goes to infinity, so this is kind of like what we did with finding the limit of a sequence. And so hopefully, because of your knowledge of rational functions and your experience, you can just look at this and immediately know the answer, that the answer is going to be -7/5. If you want to show some work here, then the thing to do is to divide the top and bottom by the highest power of x in the denominator. I always want to divide by the highest power of x in the denominator because I want to convert the denominator into a number. And then I can just look and see what the numerator is doing. So if I divide by x squared, I get 7 minus 3 over x plus 2 over x squared. And that becomes -5 plus 1 over x squared. And I think it's really helpful to actually do this step because it shows that very clearly that as x goes to infinity, this is going to 0, this is going to 0, this is going to 0 as well, and so this whole thing is just going to -7/5. Cha. Okay, good. Good. Sorry, this is a little slow. What's left? 3 more? Yeah. Let's just do them. I think you can definitely watch this on 2 times speed. Good. 15. This is the limit as x approaches 3 of floor x plus 1. Okay, what is the floor function? I think you know this from Comp Sci and also from last year. Floor x is this function which just kind of drops down to the closest integer, if it's not already an integer. So it's not truncated, it's, it's floor. So what does it look like? It looks like that, 1, 2, etc. And yeah, and then the negative side looks like this also. So it's not quite odd, but it's floor. Okay, so I guess the thing to realize here, perhaps I just want to only graph this once, and so let me just finish this graph, because this is 4, 3, and that's 2, 3, 4. Give me a second here. Cha and sha. I think I've done that right. Yeah, I have. And so now, one thing you could do is just look at this graph, or you could just kind of talk it out. But I think the answer here is that ultimately we're taking the floor of 4. And what happens when you take the floor of 4? Well, if you're a little bit less than 4, then your floor is 3. But if you're a little bit more than floor, your floor is 4. And so the answer is that this limit does not exist. Why? Well, if you're going to write down on your paper that the limit does not exist, you need to give an explanation. And here the explanation is that the limit from the left is not equal to the limit from the right. And we can now just show that this is true. So the way to do the correct way to kind of execute this problem is to actually write everything out that I'm writing now, which is to take the initiative to split this up into the limit as x approaches 3 from the left and the limit as x approaches 3 from the right. If I plug in a number which is a little bit less than 3 and I add 1 to that, then that number is a little bit less than 4. What is the floor of a little bit less than 4? It's just 3. And if I plug in a number which is a little bit more than 3, then that's, when I add 1 to it, that's a little bit more than 4. What is the floor of a little bit more than 4? It's 4. And the limit from the left is not equal to the limit from the right, and so this limit just does not exist. Let's see, that's good enough. Okay. Good. 16. The limit as x goes to negative infinity of 2 to the negative x. This is also just kind of a silly problem. Well, what does 2 to the negative x look like? It's a decaying exponential. It looks like that. And so, yeah, that's all I have to say. The answer to this is just infinity. Good. Last one. 17. The limit as x approaches negative 1 plus of x cubed plus 1 over x minus 2 times x cubed minus 7x plus 6. Whew. Well, let's see what happens. If I try to plug in negative 1, then what happens? Well, negative 1 cubed is negative 1. So, this will be 0. So the numerator is going to 0. And let's see what the denominator is doing. Well, if I plug in negative 1 here, and I cube it, I also get negative 1. And negative 7 times negative 1 is 7, so that's negative 1, and 7 is negative 6, and 6 is also 0. So I indeed have a 0 over 0 situation, and I can't quite tell what the answer is. Alright, using our extensive background knowledge on polynomials, what we have effectively just done is to plug negative 1 into this cubic, and we got back 0. So that means that negative 1 is a root of this cubic. And if negative 1 is a root of this cubic, then we know by the factor theorem that x plus 1 is going to be a factor. And therefore, we should just try to factor that denominator, and actually we will just succeed. How do I do this again? I think this is kind of the only way to do this. Cubic coefficient is 1, quadratic coefficient is 0, that's -7, and that's 6. I guess you could do polynomial long division, but one way or another you need to recognize that since, looking at this cubic in the denominator, that since -1 is a root, x plus 1 is a factor. And so, okay, I expect this to go in evenly, so I get 1, -1, add is -1, multiply is 1, add is -6. What happened? Sorry. Add, what, bring down 1, -1, add -1, multiply 1, -6, 6. What have I done wrong? Something went wrong. 7, 13. Did I copy this problem down wrong? That's very possible. X cubed -1 plus. What the heck is going on here? Sorry. Everything I've just said for the last 4 minutes is a bunch of garbage. Because everything I've just said is a bunch of garbage. Because, never mind, -1 is not a root down there. I just kind of got ahead of myself. What happens when you plug -1 in here? You get -1 cubed minus 7 times -1 plus 6. And so that's -1 plus 7 plus 6. So that's just freaking 12 down there. So this is just not a 0 over 0 situation. This is a 0 over 12 situation. And this is a super problem, and I fell for my own trick, and the answer to this problem is 0. Okay, good. That was the last couple. Went very slow, but hopefully that was thorough, and you're getting a hang of limits. Goodbye!